Okay, so last class we looked at the definition of noise figure and noise factor. We looked at noise temperature. So this class what we'll do is we'll start off with noise figure of cascaded systems. So we'll see what happens when you cascade let's say two blocks, what happens to the noise figure of the overall noise figure and how it depends on the noise figure of each of those blocks. We'll look at a couple of ways of deriving it. We'll do it a little bit of the long way and then we'll see if there's an easier way. And then we'll look at noise figure of lossy circuits. And then we'll try to do, we'll see, I don't know if we'll have time, but we'll try to do noise figure of a MOSFET. Okay, 2-port noise figure of a MOSFET. But let's start off with the cascaded noise figure. Okay, so right now we'll just do this. And we'll also look at SFDR. What is the dynamic range of the system? Okay, in this case, in the case of RF circuits, it's called spurious free dynamic range. We'll look at what that is, definition of that. Okay, so first before that, so let's start off with cascaded noise figure. But before we do that, let's see what is called the available power gain of a block. Okay, so let's say it's driven with a source Vs and resistance Rs. The load resistance is RL. Okay, so the input resistance is Rn1, output resistance is Rout1, and the input voltage is Vn. And we'll also assume that the system is matched, power matched. Okay, we'll assume that Rs is equal to Rn1 and RL equals Rout1. Okay. So now what is AP? AP is the available power at the load under matched condition at the output over the available power from the source again under matched condition. Okay. So what is Vn first? Let's calculate each of these. So first we'll calculate the available power from the source. So what is Vn? Okay, not a good way to start off. What is Vn? Vn is Vs times Rn1 over Rs plus Rn1. Okay, which is Vs over 2. Okay, we'll see. So what you'll see is in some cases we'll prefer to write this as Vs over 2. In other cases we'll prefer to leave it as a ratio of impedances, and you'll see why. Because when we consider cascaded systems, we want to bring it to a form which is familiar to us. Okay, so in this case we decide to write it as Vs over 2. And there are cases where you will replace Rn1 with Rs. There are cases where you would replace RL with Rout1 and so on. Okay. But for now we'll write it like this. What is the power available from the source? Okay, so it is Vs over 2 whole squared over Rs. Let's assume Vs and V out are all RMS quantities for now. What is V out? So that is the new denominator. What is the numerator? So to find the numerator, we need to find out V out. Do V out squared over RL. Okay. What is V out? So it's V in times. So let's assume that the unloaded voltage gain of the two port is AV or AV1 in this case. So it's AV1, okay, times okay. We'll rewrite this as Vs times Vn is Vs times Rn1 over Rs plus Rn1. We'll choose to write this as half. Okay. So the available power in the load is V out squared over RL. Okay, which is Vs squared. So we'll just expand it out. And we are going to write this as R out 1. We'll replace RL with R out 1. Yes, you can, but we'll see why we don't want to do that. Okay, the reason is we'll leave some of these factors in here because when we calculate for cascaded networks, we'll find some terms in there which can be rewritten as in terms of your AP. Okay, that's the reason we'll leave it in this form for now. Okay, in reality, yeah, if you just replace everything by half, right, and if you go back for cascaded this things with and you consider everything with half, they will cancel each other out still, but to gain some insight into how the voltages are getting transformed and so on, we'll do it this way. So what is AP? It's this over this. So okay, so it is okay, so it's Rn1 over Rs plus Rn1 whole squared times AV1 squared times Rs over R out 1. Okay, so now let's consider a cascade of two port networks. Okay, we're going to cascade two of these, and okay, let me do a slightly better job of drawing this. Okay, so this is Vs, Rs, and okay, first let's put in VRS squared. in2 squared okay, V out, and we'll also assume this has a gain. The unloaded gains are AV1 and AV2. Okay. So we'll call the input and output impedances Rn1, Rout1, and Rn2 and Rout2. Okay, so let's look at okay. So first let's look at the noise at the input of the first stage. Okay, we'll calculate the noise at each one of these points and see what happens. Okay. What is this? So we'll call this Vn1 squared. So what all components does it have? So it's going to have a component from Vrs squared, En1 squared and In1 squared. And also remember that in general En1 and In1 can be correlated. So you can't handle them separately. Okay. So you're going to have In1 times, that's the noise voltage from In1 plus En1. Okay. Okay. And you're going to take the square of this guy. Right? That's in case they are correlated. Okay, then you also have a second term. What is the second term from Vrs squared? Okay, that is the noise at input of stage 1. Okay, now let's go to the noise at input stage 2 input. It's a 50 ohm resistance, right? So you have 4 kTr delta F. This is a noise. Okay. What is this? So you have all of these times AV1 and then times the loading at the input of the next stage. Okay, so you have Vn1 squared times AV1 squared whole squared. So this is the contribution from the first stage. Okay, plus looks like I'm going to have to spill over into the next page. Okay, because now you have to account for noise from these guys En2 and In2, and it's going to be similar to this guy. So plus, sorry, yeah, yeah. You want me to drag this one? Okay, which one are you saying? Oh yeah. What about this one? Oh, you're telling me I can actually scroll up and down with this? Oh yeah, I can do that. But to create a next page, I need to use the arrow. Oh, okay. What you're saying is okay. I see what you're saying. Okay. Something like this, right? Okay. Oh, sorry. Okay, is that clear? Pretty straightforward. Okay. Now you can calculate noise power at stage 2 output. So the reason we are doing all this is so that, remember the definition of noise figure is the overall noise figure due to all sources in your system you are considering over the output noise power due to the source alone. So suppose you consider the cascade of two stages as one big stage, you want to calculate the overall noise power and then divide it with the noise power from the source alone. Okay? Yes? AV2 squared. Okay, and okay, so now let's calculate the total voltage gain. What is that? You have to take into account loading at the input, Rn1 over Rs plus Rn1, then AV1, then Rn2 over Rout1 plus Rn2, okay, and then AV2, and then RL over RL plus Rout2, okay. Sorry? Which load resistance noise? RL noise. Yes, RL noise will also come, but for now we are going to ignore that. Okay, because that will be taken into account if you cascade it with the next stage, then you would take it into account there. Okay, so this is V out squared over okay. So you can do a bunch of algebra, but I just give you the result because it's taking obviously going to take a long time to write out everything. Okay, so what you'll see is you'll get 1 plus I try to turn this off, doesn't work. Try to turn off the keyboard. over, uh-oh. Times okay, you get something like this. What is this guy? Anybody? The first term? It's the noise figure of the so this whole thing is the noise figure of stage 1 with respect to the source impedance driving it, which is Rs. Okay? This whole thing. That's pretty straightforward, right? The input noise is 4 kT Rs plus noise due to the 2 port over 4 kT Rs. Okay? So this we know is F1 with respect to the source impedance Rs. Let's look at the second term. Oh, okay, I think we're going to need that. Okay, so let's rewrite this slightly differently. Okay, before we go there, so what is F2 with respect to R out 1? It's 1 plus R out 1. Sorry. Right? This is the noise figure of the second stage with respect to the source impedance driving it. Okay? Okay, so what we are going to do is today is not a good day for this. Okay, too many times. Okay. Okay, so what we're going to do is we're going to take the second term, rewrite it in terms of F2 R out 1. Okay, because they have a number of common terms. You can see that, right? You see that it has the numerator and a bunch of common terms. Okay, so the second term we'll rewrite it slightly differently. Oh man, I didn't do anything this time. Okay, so we'll take the second term and rewrite it like this. Okay, so that's what we have so far. So right? So we have En2 plus In2 R out 1 over Av1 squared 1 over 4 kT Rs and 1 over Rn1 plus Rn1 over Rs plus Rn1 whole squared. Okay, so what I'm going to do is I'm going to multiply and divide by Rs over R out 1. Okay, look at this guy. Okay, that happens to be the power gain, okay, of the first stage. Okay, this happens to be AP1. Okay, so this means the second term is now, sorry, yes, it's 1 by AP, of course, yeah, sorry. Okay, so the second term now becomes by right, because now you have Rs over R out 1, this Rs gets cancelled, so you get R out 1 here. Okay, now what is this guy? It's F2 R out 1 minus 1. Okay, so what is the F overall? Let's go back a couple of pages. So you had F1 Rs, okay, plus the second term was what we showed that it is F2 R out 1 minus 1 over AP1. Okay, and in general you can extend this to n stages. So if you have some, let's say, m stages, F1 over okay, so what happens is if you have m stages, so it is the noise figure of the first stage plus F2 minus 1 over the gain of the first stage plus third stage would be F3 minus 1 over the product of the power gains of the first two stages and so on. Okay, so this is called the Friese equation. You might have heard of it. Actually, sorry, it's the Friese. His name is Friese. It's not Friese equation. Name is Friese. Okay, I'll put up this paper. There is a nice paper in the night. I think it's in the 1940s or 50s, the proceedings of the IRE. Okay, so I'll put it up for download. You can take a look at it. The math is very similar. Okay, so remember this. It's a very important equation. So what do you understand from this? So if you have, let's say, so this is obviously the reason why if you have a receiver, so yes, you had a question? Exactly. Why do you have an LNA right at the beginning? Why do you need a so-called low noise amplifier? Because you want to get as much gain as possible with very little noise, so that the subsequent stages, the noise of the subsequent stages gets reduced by the gain of the preceding stages. Okay, is that clear? So typically when we'll get to mixers, you'll find that the mixer noise figure could be 10 or 15 dB. Okay, whereas the specification for the overall receiver chain may be only a few dB. Okay, so what that means is the low noise amplifier is pretty much the most critical portion as far as noise is concerned. The other thing it tells you, as you keep going down further down the receiver chain, the noise matters less and less as long as you have more and more gain behind it. And that kind of makes sense to you, right? Because as you keep adding more and more gain, the signal strength gets stronger and stronger, so your SNR also gets better. So the SNR of that, the noise added by that stage becomes less and less significant. So this is, earlier we saw the IIP3 of cascaded stages, where the IIP3 keeps getting worse, okay, as you keep going down the receiver chain. So this is a fundamental trade-off in receivers, where as you keep going down the receiver chain, the linearity of the subsequent stages matters much more than the linearity of the front stage. The noise of the front stages matters a lot more than the noise of the later stages. Okay, so what I'll do is, in homework problem, I'll make you like decide the noise figure and IIP3 of a certain system. We'll take a cascade, like maybe a direct conversion receiver with 3 or 4 blocks, and I'll give you some, for some blocks I'll give you some of the parameters, IIP3 or noise figure, and you'll be asked to calculate, you can put it into an Excel file if you want, you can use MATLAB, whatever you want. You can try to trade off, come up with reasonable values for all of these. Okay? Okay. Next. Okay. Next we'll look at lossy circuits. Okay, so let's say you have an off-chip. We looked at some of these lossy circuits. We looked at were these filters. We looked at image reject filters. We looked at band select filters. So all of these are passive filters, but automatically passive usually means that they have some loss. They have some power loss. Okay, so we'll see so let's say you have a block like that with a passive circuit with a loss. What is the noise figure of the lossy circuit? Okay. So let's draw out so we can replace the lossy circuit with an Rn. Oh, sorry. We'll call it the VThevenin. This is your lossy circuit. Okay. So what is called your available power loss, which is represented by L, okay, is given by P in over P out. It's exactly the opposite. So it's assumed matched condition is assumed. It's basically 1 over AP of that. Okay. So what you'll find is, for LNAs, other things, you'll specify gain as in dB, like 15 dB or 20 dB. Whereas for lossy circuits, the loss is defined as like half a dB or 1 dB. Okay, it's actually a negative power gain. That's what it is. So what is Pn? It's Vs squared over. Assume that Rs equals Rn and Rout equals RL. Okay, so Pn is Vs squared over 4Rs. Right? What is P out? Vth squared over 4RL. okay, or R out, whatever R out equals RL. Okay, and you can also show for a general passive circuit, right? For a, yes. Okay, so we define the available power gain as P out over Pn. Yes, it's a loss, so it's a power loss. So okay, so this is nothing but the negative in dB, it's the negative of your power gain. Okay, so if you have a lossy circuit, you want to characterize the loss rather than the power gain, right? So typically you will say if you it's called the insertion loss. So you insert a filter in between, you know, inside a receiver. They'll tell you that it has a loss of 1 dB or 2 dB. I think we studied an RF switch. In some cases, if you have a time domain like a TDD kind of system, you need an RF switch. So in those cases, they'll tell you the RF switch has a power loss of so many dB. Okay, so that's the reason you would rather characterize it by power loss, and you'll see why, because the noise figure is closely related to the power loss. That's another reason why you want to define it in terms of power loss. Okay, so let's say this is a passive reciprocal circuit. You can show that the noise equivalent of this circuit is okay. The noise equivalent of this circuit is nothing but so of course the output impedance is R out. You can show that okay, this you can show for a passive circuit. Okay, so in this case, the overall output noise, okay, we'll write it in terms of VTH, R out and RL. Okay, so times squared actually. Right? And remember that your gain was this was your gain of the system, right? Okay, so what is your noise figure? Over times AV squared, right? It's the total output noise over output noise due to RS. So you take the noise due to RS multiplied by the overall gain, square of the overall gain. So this is 4 kT R out over VNRS is 4 kT RS. What is AV squared? It's VTH squared over VS squared times by R out whole squared. So this term gets cancelled. The 4 kT gets cancelled. Oops, sorry. So what does this leave us with? Times over R out over RS. What is this guy? This is your power loss. Okay. So this is a very important result for us. So if you're inserting a filter, it automatically ups the noise figure by the same amount as the power loss. Okay. So what does this mean? Remember, if you remember our receiver, before the LNA we put in a band select filter. Okay. Now what that means is, if the band select filter, if the loss of the band select filter should be as should be as small as possible, because it directly adds to the noise figure. And how do we know that? Because remember, again, if you look at the cascade, the overall noise figure is is the noise of the noise figure of the first stage plus f2 minus 1 over the gain of the previous stage. So you add noise, what it does is, then first of all the loss adds directly as noise. Okay. Second thing, the noise figure of the LNA also gets up, because now instead of a power gain, it's actually a loss. Okay, two things happen. Okay, so it's a major problem. So you need to try to minimize this the loss of these filters as much as possible. Okay, so there are some, I guess one last thing we'll stop with. One last thing we'll do, we'll find how to write your the noise figure of a system in terms of the SNR, and then we'll stop there. There are some other things. I think the alternative definitions, I'll just put up the notes, you can take a look at it. It's just, instead of if you just assume that everything is matched, right, R in, R out, everything is matched, it's very easy to derive. You just go ahead and, in 2 steps you'll get it.
So in this case, suppose we had a noise figure of, we had a SNR of 9 dBs, perhaps at the input of the filter.
Okay.
And this filter has a noise figure of perhaps 3 dB.
Okay.
So SNR at output will be 6 dB.
Yes.
Plus whatever attenuation it gives to the signal.
No, but the difference is both the signal and the noise get attenuated. Right? So if you have a certain noise at the input, that also gets attenuated through the loss. Right? Okay. So let's consider an amplifier of some available gain, AP, right? The input noise is NS and the added noise, so we'll see the additive noise is NA. Okay. What is the noise figure? It's AP times NS plus NA over AP times NS. Right, that's pretty straightforward. This is 1 plus NA over NS. Okay, so A is the noise, input referred noise of the amplifier which is added to the system. NS is the noise of the source. AP is the available power gain. It's pretty straightforward. Okay, so let's say it also comes with a signal power S. What is the input SNR? It's S over NS. Okay. What is the output SNR? It's signal goes up by AP. Okay, which is S over NA plus NS. What is input SNR over output SNR? It's okay. Okay, so if you want to write noise figure in terms of SNR, noise figure can also be defined as the input SNR over output SNR. Okay, so we'll stop here for today and continue next week, next on Monday. Now about the project, I